Welcome back. In the work power energy, if you recall, I was talking about how to prove a force to be conservative or not purely mathematically, and we did it, and I think I'm going to repeat that the curl of f, if it is 0, del cross f if it is 0, are dou fx by dou y is equal to dou fy by dou x. Dou fz by dou x is equal to dou fx by dou z, etc. Then we say the force is conservative. And whenever the force is conservative, or whenever the curl of f is 0, f is always expressible as a plus or minus gradient of a function, a scalar. Because remember, gradient is always defined only for a scalar, not for a vector, because gradient itself is a vector. If you have 2 points, say the temperature, say 30 degrees, 40 degrees, how is the temperature gradient directed? From lower value to the higher value. You always remember this. It is always directed towards the increasing value. Alright? Okay. Now, and then when you talk of force, we say that we are going to get potential energy. And I have shown you how to get force if you have potential energy given, or how to get potential energy if force is given. Alright? Then, I was trying to give you a very important concept, in this work and energy, that a body, if it is displaced in a fluid, if it tends to regain the original position, but not before performing quite a few oscillations, is called stable equilibrium, in which case the potential energy there is supposed to be minimum, but net force 0. That means it is an equilibrium. That is called stable equilibrium. I have shown it to you. The second one is neutral equilibrium. If I try, there also there is equilibrium, but if I push the body to some point, and the push, if it is depending on its intensity, it will go to certain extent and then stop it. That's called neutral equilibrium. There the potential energy is constant throughout, no difference in potential energies. And there won't be any restoring force. There won't be any restoring ability. Alright? Then the third important is the unstable equilibrium. If you try to displace a body slightly, it moves on and on and on. We call it as unstable equilibrium. In the beginning, that net force is 0, but not beyond that point. So in all the 3 cases, what is common? Sigma of 0. That is, they are all in equilibrium. Then second point, stable equilibrium, potential energy is minimum. Unstable equilibrium, potential energy is maximum. Now if you go mathematically, when you say potential energy is minimum, I have shown that to you yesterday, in the previous class, that the first derivative of potential energy must be 0 and second derivative must be positive. And if you convert that in terms of the force, it is reversed. Alright? So you have to be very careful. I gave you all the details, and then I went on to give how to identify the stable and unstable neutral equilibria if force as a function of distance is given. So I have shown you this. If the slope here is positive unstable, negative stable, and 0 means neutral. That's how it is. And then if you are given u versus x, be very careful about that. And you need to identify local maximum, local minimum. Minimum is characterized by your stable equilibrium. Highest is maximum is characterized by unstable. Constancy is characterized by neutral equilibrium. This is what I intended to tell you the other day. Okay? I hope things are clear to you so far. So, from this, one very important thing you should always remember is what? What? Potential energy is defined only for conservative fields or conservative forces. How to get the potential energy expression? I told you that delta U is minus Fc dot dr. Okay? This is how it is. Now, in the case of gravity, what is F? F is equal to gmm by r square. Gmm by r square. That is a gravitational force, and here m is mass of the planet. This is the small r is the distance from the center. The whole body is treated as though it is a point mass because of spherical symmetry. A point you will understand much later. And I am placing a small body m over there. Okay? Now this is what? Now, when I am going to substitute this, and when you are going to put your limits, then you better define your potential energy, which we call as gravitational potential energy. You know, how is this gravitational potential energy defined? Amount of energy required to bring, very important, two bodies from infinite separation. Infinite separation to current separation. Now this is very important. Very, very important. Remember. Okay? Now you see that energy required to bring two bodies from infinite separation to current separation. Now let us say this is Earth, the planet is one body, and let us say it has its own zone of influence, which we call as infinity, right? Now if this is infinity, from here I am now I want to bring it to current separation R, where from infinity to current position. Now, first of all, see, gravitational force is attractive force. So, energy required to bring, what do you mean by that? From infinity, if I am just coming into the gravitational influence, then the body would automatically come. You need not have to spend any energy. On the contrary, if you take body from current separation to infinite separation, then you have to do work, you see. You have to forcibly take it away from this gravitational force. Therefore, you have to perform work. You get my point? Well, this is very crucial. Try to understand this concept carefully. Now, in the case of attractive force, energy is required to take from current to infinity in the case of gravity or in the case of attractive forces. All attractive force. For example, you take the case of a powerful magnet with North Pole here. As usual, it has its zone of influence. And if I take a unipolar magnet, you don't have unipolar magnets, but then do take it right. Sorry. South. South pole once again is automatically attracted. But if I have a north pole here, there is a repulsion. So for me, I have to do work against this force. Therefore, I am able to store some energy. You get my point? If there is a repulsive force, then I have to really perform work as per this definition. But as per the same definition, if I have an attractive force, in the reverse you have to do the work, but in this process, energy is released. That means the potential energy change here is bound to be negative. In the case of repulsive force, it is positive. Generally, you are free to choose reference level of potential energy to be zero at any level of your choice. I am now taking you to be zero there. There is no connection there for potential energy zero, just like that I am saying. And when I am allowing the body to fall through, it's releasing energy. And if I have to take it from here till here, that means what? From this difference to this difference, I would say potential energy. Actually, you cannot say potential energy at any point. You can only talk about the difference. Since I have taken the potential energy at infinity to be zero, and here the difference is negative, therefore the value here is bound to be negative. So anywhere you go, once you take u as zero, the potential energy is negative. Now here, this is the concept I was trying to explain to you the other day. Never get carried away with the meaning of negative. There is nothing like a negative energy. I mean, it all depends on how you speak. I told you in the beginning. Now, how much of money do you have? Each I have got minus 2 lakhs with me. That means he has taken a loan of 2 lakhs. So that minus, see, either you have money or you don't have money. What do you mean by saying you have negative money or positive money? I mean, it doesn't carry any meaning, but then if you understand the mathematics and if you understand the logic there, then you can easily say, yes, negative means this. All depends on how we understand. That's it. In a much similar way, potential energy also. You get my point, right? So the potential energy is negative for all attractive forces as per this definition. Now they may ask you at any stage, what if potential energy is defined in the reverse way? It is a hypothetical question. Remember, it's a hypothetical question. What do you mean by that? Is it required to bring two bodies from current separation to infinite separation? And in the case of attractive forces, I have to do work. You get the point? In the case of attractive forces, current separation, I have to take it away. I have to do work. So potential energy is stored there. In which case, attractive forces have positive potential energy. Now that I think you can understand that. When I say the reverse, attractive forces will have negative potential. It is the difference that comes. Minus 100 to minus 150. Final minus initial. That's all. Final is 150. Initial is minus 100, minus 50. The change, that means the potential energy has decreased by 50 units. What happened to all that is something that you have to find out afterwards, not at this stage. Therefore, we understand negative as something which is conceptual. There is nothing like a negative potential energy at any stage. That is clear to you now? Therefore, in the case of attractive force, I am now taking, say, from here to a small distance dr. Okay? Then what do I get? Gmm by r square dr. Dot dr is positive there, is this right? So negative cos 180. This is the potential energy. Negative sign, why I am not keeping? Because you remember that is what against that. You get my point, to indicate that I have given. Now let us see. Gmm, cos 180 is minus 1 minus dr by r square. And this is r raised to minus 2 plus 1. So this is plus Gmm by r infinity to r. So that is against the force, so minus sign there. So this becomes plus, this becomes plus, this becomes minus, infinity to r. Therefore, the potential energy expression for gravitation is universal minus Gmm by r. Never forget this. Now what is important here for you, I'll tell you, this is your body mass m, this is capital R, I am taking it to be infinity, and this is r. I take from r1 to r2, that means minus Gmm by r, r1 to r2, substitute minus Gmm by r2, Gmm by r1, so this is this is the change in potential energy, gravitational universal relation. Now you have to understand this, that it could be positive, it could be negative. What are the consequences of that being positive or negative? I am going to discuss that as the situation arises. Suppose from surface to a height h. Now this is where most of the people get confused. I'll give you this. This is standard. We are going to use the capital R we use for radius of curvature of the planet. H is height from the surface and small r is from the center to the point P. Therefore, R is equal to R plus H. I want to take the difference between the surface and a height H. So what do I do here? What is the initial thing? Surface is R. To a height H means R plus H. So you have by R into, so R gets cancelled. Gmm by R, I am taking common. This is the change in potential energy from surface to a height H. H also you bring it to the denominator. What will happen? By H. So what do you get? Gmm by R square into 1 by H plus 1 by R. This is the change in potential energy from the surface to the height H. If I take surface to be 0, then this is a positive. That is the potential energy there. All depends on what you take. Okay. Now, we know very well Gmm by capital R square is the force right on the surface. And this will result in an acceleration due to gravity G naught on the surface. Therefore, G naught is Gm by R square. So I can replace this if surface P is 0, then U at H is positive. I told you, copper, infinity 0, that is negative. Surface 0, that is positive. So, potential energy at H is equal to this. A very, very standard expression for potential energy. Never say mgh. This is dangerous. That too, I am talking of surface to a height. Hereafter, I have to be very, very careful in trying to give answers to the conceptual questions. I can't replace the same thing wherever you like it. You see, it depends on R1 to R2. The G is completely different there. Now, if H is far less than R, that means, that is, what do you mean by far less than R? Very close to the surface, maybe up to few hundred kilometers, maybe 200 kilometers. You need not take a variation of G to have a very great value. Therefore, 1 by H is far, far greater than 1 by R. So, U at H is equal to mg naught by 1 by H. This is a highly specialized expression. You can't use it wherever you like it. One has got to specify that, look, this is dead close to the surface, then only we can use this, otherwise not. But in most of the cases, of course, they do take very close to the surface. So we are justified in taking mgh. Okay? And that too, I am telling you, if I consider surface U0, and infinity, what is the infinity value? This is 0, you have it, minus dmm by R, say R to infinity. What do you get? Minus, if you remove, it becomes R. So this will be Gm by R. Zero, very, very close to this mg naught H.